Welcome to RTL Audio Lab. This is Isaac, and in this video we will go over the implementation of a debouncer module for the mechanical inputs of our FPGA audio processor. We will start by describing the problem of bouncing inputs and the idea behind the debouncing logic. After that, we will discuss in detail how the Debounce FSM works and how it is instantiated within the Debouncer ZedBoard module. Finally, we will take a look at the code and the elaborated design. When working with mechanical inputs like buttons and switches in our FPGA design, we need to be aware of the issue of bouncing. When activated, a switcher button will not cleanly transition from high to low or low to high. Instead, it will bounce between the two states for some time before settling into the one the user has selected. Though this bouncing is too fast to be perceived by human operators, it can easily be detected by high-speed digital circuits. The logic in our FPGA will identify this bouncing as intentional inputs and might react in unexpected ways. The solution to this problem is to use a debouncing logic that detects a change in the physical inputs to the FPGA pins, waits until the debouncing period is over and the input signal has settled into its correct value, and then generates an output with the same value as the stable input signal. We can then use the output of the debouncing logic as the input to our system. One way to debounce signals is by using a 4-state finite state machine, or FSM, which works as follows. The idle state is reached after power-up. Here the FSM resets the counter and the signal output, and then transitions to the edge-detected state. The edge-detected state is reached after the idle state at power-up, or whenever the output of the debouncing logic is different than its input. In this state, the FSM counts to a programmable number of clock cycles, after which the input signal is assumed to be stable, and the FSM transitions to the corresponding state, either debounced high or debounced low. The bouncing period can vary depending on the type of mechanical element and the analog components used to interface with the FPGA inputs. 10 to 20 milliseconds seem to be the accepted rule of thumb. The debounced high or debounced low state is reached after the input signal has settled in either a high or low state. In these states, the output of the debouncing logic is set to the value to which the input signal has settled. The FSM remains in the debounced high or debounced low state until the input signal changes, in which case the FSM transitions to the edge-detected state. This FSM can be made more efficient. There is no need to have separate debounce states, and the idle state is only reached on startup, so it could be removed as well. Having said that, we are not going for maximum efficiency here, so we'll leave it as it is. The Debounce FSM is a generic, parameterizable core that can be used for debouncing the inputs of any FPGA design on any board. It makes sense to create a module that instantiates as many Debounce FSM cores as required for specific hardware and connects them properly. This is the job of the Debouncer ZedBoard module. This module receives the signals from the physical switches and buttons on the ZedBoard and generates a debounce version of each of them, which can then be used as inputs to our logic. Here we can see the RTL description of our Debounce FSM. In the I/O we have the clock signal, the debounce counter, which we can use to adjust how long the FSM waits for the signal to stabilize, the input bouncing signal, and the output debounced signal. We then declare our internal counter and the FSM state signal, which gets initialized to the idle state. The Debounce FSM module also includes clock domain crossing logic for synchronizing the switch and button inputs to the clock domain in our design, thus avoiding metastability issues. Now we get to the core FSM logic. In the idle state, we set the debounce counter and the output signal to 0 and immediately transition to the next state. In the edge-detected state, we increment the debounce counter until it has reached the value that we set at the input. When that happens, the debounce counter is set to 0 and the FSM moves to either the debounced high or debounced low state, depending on the value of the input signal. In the debounced high or debounced low state, the debounced input is set to the corresponding level. In the Debounce ZedBoard module, we have one input-output signal pair for each button and switch on the board. Here we declare arrays that group the bounced and debounced signals for the switches and buttons, and then we assign them to the inputs and outputs of the module. These arrays allow us to control the instantiation and connection of the Debounce FSM cores according to the parameters that we selected for the module. Finally, we can see in the elaborated design that 13 instances of the Debounce FSM are generated within the Debounce ZedBoard module, corresponding to 8 switches and 5 buttons on our ZedBoard. That was the Debouncer, the first of the top-level modules that we introduced in our first video. If you would like to know more about this project, you can go to rtlaudiolab.com, where you can find sources and project files to try it for yourself. In the next video, we will take a closer look at the second top-level component of the FPGA audio processor, the clock generator. Bye for now.